Hello, we're going to be doing standard 4.1, which is on two-particle systems, and I'll be looking at problem number 2 from this section that Josh Grossman suggested. And part 8 about this problem asks us to do the following: to use the s squared operator, which is equal to sx squared plus sy squared plus sz squared, to write the matrix representation of the operator s net squared for a pair of spin 1 particles. Now we have already done this in class for a pair of spin 1/2 particles. We didn't go through all the calculations, but we did look at the final result, look at the eigenvalues and possible eigenstates of this operator, and do some analysis on what this actually means for a pair of spin 1/2 particles. And now we're going to be going through the full calculations and doing a similar analysis to look at what this operator actually does. So the desired operator that we would like is as followed, and we can use this information here to get that s net squared is equal to s net x squared plus s net y squared plus s net z squared. We just take the corresponding components, take this operator and take the net operator, and then square each of them and add them together. And to get each of these, we just use the following formula for the net. So we have s net I, where I can be x, y, or z, that is equal to s1i plus s2i, and these are equal to the following, which is S sub I tensor product with the identity matrix plus the identity matrix tensor product with S sub I. And now that we do this, we can go through the calculations for each of these before we square them. And I don't have all the math done out because it does get kind of messy, and we have a lot of calculations to look forward to already. But we should note that since these are tensor products of two 3x3s, when written out fully, they're going to be 9x9 matrices. But, so you ask, oh, why do I have 3x3s? But the reason that is because I decided to write it as a 3x3 matrices of 3x3 matrices. I wrote each entry as a block, and each block is a 3x3 matrix. And this makes the calculation simpler until we have to do the final calculations at the end. So for each of these, we can represent s net sub x as the following: h bar over root 2 times the matrix sigma x identity 0, identity sigma x identity 0, identity sigma x. So like I said, I is the identity matrix, 0 is the 0 matrix, and sigma x is the corresponding Pauli spin matrix for the spin 1 particle in the x direction. And for s net y, we have a similar setup, but it can be represented as I h bar over root 2 times sigma y, negative I, 0 I, sigma y, negative I, 0 I, sigma y. Once again, we have the same correspondences, but here sigma y is the corresponding Pauli matrix for the y direction instead. And lastly, for s net z, it can be represented as h bar times sigma z plus I, all the way down the diagonal. So this is just a diagonal matrix with those as the entries. And now that we have this, we can square each of these and look at adding them together to get our final matrix as we desire. So this gets a little messy, but I have written out the following squared matrices, which I did using computer software. So we have s net x squared, which is equal to h bar squared times this following matrix. You'll notice it is symmetric, which is a good thing. And each of the following are going to be symmetric as well, but due to the negatives and how closely related these two matrices are, we expect to get something similar for s net y squared. And we get the negative here because we had an I squared. But now we just have these entries on the diagonal and really close to the diagonal. We have them all negative now. However, in absolute value, these two matrices are the same. And we expect to get a diagonal matrix when we square this because it's just going to be all the entries squared. Because in addition to this being a square matrix, a diagonal square matrix with each of the entries, which each just in the form of having 3x3s as the entries, but individually each of these matrices is also square. So this is going to be a large, or each of these is diagonal, so this is going to be a large diagonal 9x9. So we expect this to be a diagonal matrix as well. So we have h bar squared times 4, 1, 0, 1, 0, 1, 0, 1, 4 down the diagonal and 0 elsewhere. So if we add these all together, do a bit of calculation to get it, we get that S net squared is equal to H bar times this matrix here, which is close to diagonal, except we have these 8 entries, 2 off the main diagonal, and each of those are 2. And now we want to show that their joint state can either be a singlet corresponding to a spin 0, triplet corresponding to spin 1, or quintuplet corresponding to spin 2. And we did similar analysis, like I said before, for the spin 1/2 particles, for a pair of spin 1/2 particles. So we'll note we can do the same thing, where we have that S is equal to the magnitude of our spin is equal to H bar times the square root of S times S plus 1, where the S is equal to the different spin values. And this means if we square both sides, we have that S squared is equal to S times S plus 1 times H bar squared. So our eigenstates of this corresponding operator that we're working with should correspond to the possible magnitudes of the spin measurement of the joint state, like we said. And the computer software gives us that there are 3 eigenvalues for this, and they're going to be 0, 2, and 6. And the multiplicities of 0 is just going to be 1, multiplicity of 2 is going to be 3, the multiplicity of 6 is going to be 5. And when we did a pair of spin 1/2s, we got a singlet and a triplet, and the eigenvalues corresponded to 0 H bar squared and 2 H bar squared. So I should note here that these eigenvalues here should each have an H bar squared corresponding to them. So that's my bad with the tech there. But in order to satisfy the above equations, it shows that there is a singlet state, H corresponding S equals 0. So the only way that this S squared would be satisfied would be as S would be 0. That would give us this one. And there's going to be a triplet state for 2. So if we plug in 1 here, we're going to get 2H bar squared. And similarly, if we plug in spin 2, this is going to give us this quintuplet state, which is going to be 6H bar squared. And we can kind of like talk about briefly what this actually means physically. For the spin 0, we just have this like probabilistic region at just 1 point. But when we have spin 1, we have this triplet state where it can either be a disk around the center, or it can be these 2 cones going up and down these probabilistic regions where the spin could be at the state. So we have 3 eigenvectors corresponding to these 3 different regions. And it's going to be a little more complex, but we're going to have a similar thing with like 2 different cones going up and down and this central region for spin 2. And these are going to correspond to the 5 eigenstates that go with this eigenvalue. So that'll be it for my analysis on these joint states here. So thank you.